So part 3, we kind of step back again from the whole ions, the metals forming cations, losing electrons, and the nonmetals picking up electrons, forming negatively charged anions. And we're going back to the neutral atoms. Okay, so part 3, the neutral atom, of course, we have the nucleus. And outside the nucleus, we have the electrons. And when we talk about size, one of the things about the electrons is it's actually what gives the atom volume, because the nucleus is really small, but it's that electron cloud that gives the atom volume. Okay, so how big is an atom? And my computer's kind of got a mind of its own. Postpone. There we go. Okay. So if we took the group A, main group and group A, those are synonyms. So the group A elements, so that would be what, the S block and the P block elements, shoved them together. Then with regard to size, this shouldn't be so surprising. If you're going, size increases in the group as you go down. Okay, that makes sense. The atoms get bigger. This other one, I'm going to have to kind of talk about coming up. This one's a little bit counterintuitive. There are some things in science where you think they should be this way and say, okay, it's just backwards, so this is just backwards. So notice this says as you're going, let's see, increases. So as you're going from the right back to the left along the same period, it gets bigger. Okay? So, well, like chlorine is smaller than sodium, because chlorine and sodium are in the same period. Now, I don't think that makes sense, because chlorine has 17 protons and 17 electrons, and sodium has 11 protons and 11 electrons, but sodium is bigger. Yeah. But I'm going to kind of explain why that is. Okay. That's why I said counterintuitive. But if we kind of pick on the sodium, like potassium would be bigger than sodium, rubidium would be bigger than sodium. Okay, so that kind of makes sense. Those two trends. Okay.
Does that change the density kind of property? If it's like, because these seem to be heavier, but if they're less
I
large?
think density is more, not on the atomic level, but
Okay.
more of the
Okay.
kind of the intermolecular bonds, how it's going to pack together.
This density kind of, we would use water as kind of a model for how dense an object is on the on things that we can observe.
Yeah, kind of middle of the road. Although water has hydrogen bonding, which is kind of unique to other compounds and substances. And so actually that adds to kind of how fluffy it is. So I don't know if that's a good example or not. Density, like how squished, you're on the right track. Like how squished together the atoms are isn't necessarily directly a function of their electron cloud, which is actually what we're talking about.
Okay.
Yeah. So we have, and I never really looked much at the slide, but today I finally looked at it a little bit. But this is sodium in its gaseous state. This is just a figure from your textbook. This is sodium in its solid state. And here we're actually focusing on sodium in which an electron has been transferred, and it's formed a +1 cation. Okay. So we do have kind of some different radiuses of the atom. This is from the nucleus out, gives us our atomic radius. So in its solid state, which is what we say covalent bonds, or wait, metallic bonds, it's the radius is 186. As a gas, it's 157. And hopefully not so surprising, and actually we're going to talk about this in part 5. The radius after a sodium thing loses an electron, becomes a +1 cation. Now it's very, very small because it lost an electron, and that's what's giving it volume. So these are the S block. Can you see the S block and the P block here? So this is S, and here is your P block. Okay. Minus its P block minus group 8A, which of course would be your rare gases. Quade's making funny faces back through. He's got his little. So So this is kind of an interesting little thing. Again, removing group 8A or the rare gases. This is period 2. This is period 3, period 4, okay, period 5, period 6. Yep. So what it's doing is, as you go across the periodic table, increasing the number of protons, notice that, let's see, what example did I use? I used chlorine and sodium. Here we go, chlorine and sodium is all right up here. Chlorine, sodium. Okay, they're in the same period, and the one at the beginning of the period is larger. Okay? So that's kind of how that goes. So the idea that, for instance, if you pick on sodium and potassium and rubidium, the group 1A elements, the idea that as you go down the same group, the atom gets larger because you got a boatload of electrons piled on, and that's electrons give you your atom volume. That makes sense, okay? Now this other trend of decreasing as you go from left to right, so like sodium is larger than chlorine, that actually can be explained with something called effective nuclear charge. I'm going to kind of talk about that coming up. So I mentioned it's the electrons that kind of give the atom volume, okay? But there's a couple things going on with electrons. With electrons, actually the electrons are attracted to the positively charged nucleus, okay? So unlike charges attract each other. So that would, if they're attracted inward, that makes it smaller, the atom smaller. The other thing that's going on is electrons amongst themselves are repelled, okay? So this repulsion actually would make it bigger, make it fluffier. It's all about the electron cloud. So we have those two things going on. They are noisy out there today, aren't they? Okay, so if it is kind of this two things going on, if attractive forces increase, okay, that makes it smaller. So actually, when I talk about effective nuclear charge, that's what's happening, for instance, between sodium and chlorine. The attractive forces actually are getting stronger as you go across the period. If the repulsive forces are winning out, that means it's going to get larger. That makes sense. I like when things make sense. They don't always make sense. So picking on the period we've been picking on, what's that, period 3? Okay, begins with sodium and ends with argon. Before argon we have chlorine. This actually is, these are atomic radii, so these are from the nucleus out to the edge generally of the electron cloud. And the units are in picometers. Picometers, if you're a Pokemon fan. Okay. So notice that I said the trend is for atomic size to decrease from left to right, but only for the main group elements, the group A elements, the S block and P block. The transition elements have a little bit something kind of different. So this is actually now including the transition elements. We have the B elements down here, beginning with the third column there. And you can kind of see it dips down and then kind of goes back up a little bit. So we don't include them in the trend. Okay, so effective nuclear charge has the symbol Z star, kind of like in astronomy we have Sagittarius A star, which is the center of our Milky Way galaxy where the black hole is located. But Z star, you can calculate the effective nuclear charge for any atom. And I'm going to kind of walk you through it here in a minute. I think I'll go ahead and do that now. I have this little animation thing I put together. Effective nuclear charge. Looks sort of like this. So I'm going to pick on two elements that are in the same period. I'm going to pick on magnesium and I'm going to pick on phosphorus. I'm going to show you how effective nuclear charge comes in to make what? Magnesium bigger than phosphorus? Okay. So magnesium has 12 protons and it has 12 electrons, and they are configured something kind of like this. We have 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, and it peters out with 2 electrons in the 3s. So those are the valence electrons. Okay. So the non-valence electrons, we actually call them inner electrons, and actually they, what we say, shield the nucleus from the valence electrons. So coming up with the effective nuclear charge, Z star, is just a simple subtraction. And what you do is you take the number of protons, and from that you subtract the number of electrons that are shielding that nucleus. So those would be your non-valence electrons. So in this case, it's 12 protons minus 10 shielding electrons. So the effective nuclear charge is a +2. And what that means is basically those 2 valence electrons feel a tug of +2. And I kind of think of them as kind of an independent. The one feels a tug of +2, and the other one feels a tug of +2. So that's kind of what we got going on there. Okay? So that's it for magnesium. And I'll kind of show that attractive force like this. Z star is +2, and I've drawn green arrows to kind of show you that attractive for the attraction of the 2 valence electrons for those the effective nuclear charge of +2. So now let's switch gears and go with phosphorus. So phosphorus has 15 protons, and if it's neutral, which it is, we're going to go with 15 electrons. It's configured 1s2, 2s2, 2p6, and then we go to n is equal to 3, and we have 3s2 and 3p3. So that's what that looks like. Notice that actually both of these elements, they're in the same period, and maybe not so surprising, they have the same 10 shielding electrons, the same inner electrons. So if we calculate the effective nuclear charge for phosphorus, it's 15, plus 15 because there's 15 protons, minus 10 because there's 10 shielding electrons. So the effective nuclear charge is +5. So think of basically that nucleus as having a more of a powerful, instead of +2, it's +5. And think of each one of those valence electrons. There's 5 valence electrons, 2 in the 3s and 3 in the 3p. They're individually being attracted to that +5. Well, +5 is stronger than a +2. So if I were to kind of use kind of the length of the arrow to show that attraction, it would kind of look like this. So I just drew my arrow very thick for my second scenario, where the effective nuclear charge is +5 instead of +2. So that makes it smaller. I finally this has been something that's hard for me to explain, and so finally I'm just like, you know what, I'm just going to chase that down. So there you go. Consider it chased down. So that's why as you go across, your effective nuclear charge increases and it gets smaller. Oh, come on. Okay. So this will be due on, Monday. Marvelous Monday. It's not after Thanksgiving, it's just plain old Monday, isn't it? And this is what those look like. I think you'll be fine. Okay. So for each of these pairs, and actually usually on your unit exam, I think this is what I do. I get you guys mixed up with my intro students, but I will ask you questions about which one's larger. And so my advice was to find them on a periodic table and say, okay, which one's larger. For 11, explain why the radii of atoms do not simply increase uniformly with increasing atomic number. And it's back to that, and in purple I say size is a balance between attractive and repulsive forces. If you just want to write that down, I'm fine with that. So I'll push these out there, and I've had this effective nuclear charge Z star there. Hints for 12, I don't know. It says that the masses of atoms can be determined with great precision, yet there's uncertainty about the exact size of an atom. And to me, that kind of goes back to, remember we said that Heisenberg said, we know that electrons exist in orbitals, and orbitals have energy and it's kind of a specific location associated with them. But there's play in that location. So you cannot know both the energy and the location of an electron at any given time. So something like that. Don't think too hard about it. For 13, which is, there's two parts, which is, in one case, the smallest atom in group 13. Let's see, group 13, we don't usually do that, so group 13 would be, do I have my 13s on there too? Yeah, good. So, yeah, 13 is 3A. So you can do that. And then the smallest of these. And then I think, I don't know if these are in the same period. I don't know, but you got the idea. SB, SN, yeah, they, PO, stretching. No, I don't think they're in the same, yeah, they are in the same period. I see strontium. They all look like they're in period 5 to me. So I think you'll be fine. Okay, so now back to part 5. Yeah, we can't call it a day. It's tempting. Let's see. Part 5 was where we just did one slide, then that's all we had time for.
One of them was in group 6, the PO.
What's that? Polonium?
That one, there were a bunch of them in 5, but then the one PO was in 6.
Yeah, the other one were in 6 too, I think.
Oh, okay.
Period 6.
I did these, and then that one.
Oh,
Okay.
oh, this is in 5 and that's in 6. Okay, thank you.
I just wanted to make sure.
Yep.
I was right, okay.
Well, I would have to double check the question. But I think you're right. I think you're right.
Okay.
When will our test be?
What's that?
When will our unit 4 test be?
Your Unit 4 test is the 8th, December 8th. And then we, well, at some point we'll start lecturing Unit 5 material, which is gases, but there is no unit exam over gases. But we'll do a gas lab on the 15th, of Thursday, and then we segue into finals week after that, I think. Yeah. I know. Okay. Oops. So we did this first slide, right? We're switching gears now from neutral atoms to metals kicking off electrons to become cations, and nonmetals picking up electrons to become anions. So we kind of did some of this in lab on Thursday. Actually, a lot of this, I'm like, oh, we talked about that in lab, didn't we? So one of the things, I'll put all these up here. Do you remember in lab I said if you want to just quickly know how many valence electrons a main group element has, you just look at its group number, the number before the A. So for instance, the halogens are 7A, so they have 7 valence electrons. So fluorine is a 7A, and you see the 7 dots around fluorine. These are like electron dot structures. And after Thanksgiving break, we'll talk more about Lewis dot structures, and these are kind of a precursor to Lewis dot structures. Nitrogen is a 5A element. You can see those 5 valence electrons. Okay, oxygen 6A, 6 valence electrons. Of course, we said it's all about the octet, right? So they all want to get 8 valence electrons like neon. So helium would look like this. Helium's atomic number 2. So it has 2 protons, 2 electrons, and this is what they look like. It's what, 1s2? Okay. Sodium, okay, it's a 1A element. It actually has 11 electrons. 1A means it has one valence electron, so it would look like this, right? Sodium, we said all the 1A elements, metals, tend to lose one electron and become a +1 cation. So it would look like this. Now the new sodium species, the Na+1, now actually it gained a new octet, but its octet actually is in the N-1 subshell. We'll be talking about that in a minute. But the one, this is kind of confusing. This guy right here is 1s2, 2s2, 2p6, 3s1, okay? So the one electron to go is this one right here. It's the valence electron. So now when we redraw this right here, these octet is right here. Here's your 8 from the 2s2, 2p6. All right, nonmetals pick up electrons to get a complete octet. They're easier for me to see, I think. Here you see the neutral fluorine atom, group 7A, 7 valence electrons. It picks up 1 electron and it becomes a -1 charge. So in lab on Thursday, we said you can hang your hat on those 7A elements, those monoatomic atoms, being a -1 charge. And that's kind of what's going on there. Sulfur, another nonmetal, it's a 6A element. It needs to pick up 2 electrons to get an octet, and in doing so it runs around with a -2 charge. So with the nonmetals picking up electrons, they become like the rare gas at the end of the period. So sulfur becomes like argon, okay? And this is like, we talked about this, so I didn't think it'd be too painful to go over it on a Friday. This idea that monoatomic ions, that was in Thursday's lab, that was parts 1 and 2, just one atom. One atom losing electrons, become a cation, gaining electrons, become an anion. And then there are polyatomic ions. A cation is something that is deficient with electrons, and anion is something that has extra electrons, positively charged and negatively charged, respectively. So, I think some semesters for the Unit 4 exam, I've given you, I want you to write how electrons are configured for neutral atoms, like you did already in homework. And I also want you to be able to say how electrons are configured for the monoatomic ions. Okay? So, 1A forms a +1 charge, 2A forms a +2 charge, and 3A forms a +3 charge. Now this is the 3A metals, remember. So it's under the JAG. Okay. So I feel like we kind of already did this. Remember a minute ago I said sodium looks like this? So sodium has 11 electrons. Neutral sodium atom, you would tell me 1s2, 2s2, 2p6, and then you go to 3s1. So the rule is that when it kicks off an electron, it's going to be the valence electron. So we've been talking about valence electrons are in the highest end, and the highest end is 3, so we have 1 valence electron. So simply then, if I was going to draw or write how the electrons are configured around a +1 sodium atom, +1 sodium cation, I would find homes for only 10, not 11 electrons. And the one missing would be the 1 electron in the 3s. So aluminum is atomic number 13. So the 13 electrons look like this. 1s2, then 2s2, 2p6, and then 3s2, 3p1. So again, identifying the highest n is equal to 3, and then basically focusing on the electrons that are in those 2 subshells. Looks like we have 3 valence electrons, and that's great because aluminum is a 3A element. So when it loses 3 electrons, those are the ones to go away. Now, I'm going to introduce a term here in a minute called isoelectronic. Isoelectronic. Iso, I think, meaning the same. Iso, because this is what it means. Isoelectronic, electronic meaning something to do with electrons. But do you see where both the Na plus 1 and the Al plus 3 have the same set of electrons, configured the same way? And they're actually they're isoelectronic with, guess what? Neon, which is also 1s2, 2s2, 2p6. So they're all 3 of those would be isoelectronic with each other. So when an atom loses its electrons, it will always lose its valence electrons. Okay, and if there is a choice, like technically, I can put it this way, technically aluminum lost 3 electrons and 2 of them that were in the 3s and 1 of them was in the 3p. Okay, so going back to something we talked about before, S has an L value of 0. I'm always in the way. And P has an L value of 1. So if we could see it in a stepwise fashion, which is really weird for me to think of, all this is saying is these will be the first to go, the lowest L value, and then these, which is kind of strange, I think, because they all 3 go, but it's true. Okay. So so aluminum you can hang your hat on. Sodium you can hang your hat on, okay? Something you cannot hang your hat on is iron. Iron has at least 2, what we call oxidation states, 2 cationic forms. It can lose 2 electrons or can lose 3 electrons, okay? So now on your test, if I ever ask you for how are electrons setting for an ion, I would always ask you for the neutral atom too, so you can kind of see them next to each other. I think that's only fair. So for the neutral iron atom, 26 protons, 26 electrons. This is how they are configured using the lowest n plus L rule, okay? And then this is basically taking that same configuration and unscrambling it to make the highest in order of increasing n. So you move the 4s2 out. And I said you don't have to unscramble it, but you can, because then you see what your highest n value is. So we have 2 electrons in the 4s subshell. So the Fe plus 2 is pretty obvious. Okay? So if you compare the neutral atom and the one that has lost 2 electrons, notice the 2 electrons that were lost were those 2 electrons in the 4s. Now, stepwise, it's going to lose 1 more electron to form a plus 3 cation. Now our highest n is equal to 3, but here we have an L value of, I said that wrong last, didn't I? The highest L value. Ugh. We have an L value of 0, an L value of 1, and an L value of 2. Remember, S is 0, P is 1, and D is 2. Yeah, a minute ago I said it wrong. It's the highest L value. So actually, on the next slide, you're going to see that one of these guys leaves. So here it is, without further ado. When it loses 1 more electron from being a plus 2 cation to a plus 3 cation, the one to leave is the highest L value. Final answer. Sorry about that. And I'm hoping that the whole D5 makes you smile, because D has 5 orbitals, 5 boxes, and a 5 is exactly half filled, and it's a very stable sort of situation. So that's favored too. Okay. All right. So metals lose electrons and become positively charged cations. Nonmetals pick up electrons and become negatively charged anions. And you can hang your hat on 6, 5, 6, and 7, what those nonmetals are going to do. So this is kind of what you guys were working with on Thursday. You guys found your 5A nonmetals, and you put a -3 at the top of that. You found your 6A and put a -2. You found your 7A and put a -1. Because 3, 2, and 1 are the number of electrons they need to pick up in order to get an octet. To get like the rare gas in their period. So these are pretty straightforward, I think. So chlorine, 7A element, actually the 7 electrons beyond neon are configured 3s2, 3p5. So neon, 10 electrons, and then we have 3s2, 3p5. So if it picks up 1 electron, as 7A elements do, notice now that 5 is going to change to a 6. So we have neon, 3s2, 3p6. And phosphorus is in the same period. So for phosphorus, it's a 5A element. So actually the 5 valence electrons beyond neon looks like this. Neon, 3s2, 3p3. And we know that 5A nonmetals pick up 3 electrons, and the 3 electrons are going to go right there in the 3p subshell. So the phosphide ion, right, is neon, and beyond neon, it's 3s2, 3p6. Cool. Isoelectronic. So the example I showed you before with the aluminum and the sodium, okay, losing electrons to become isoelectronic like neon, okay. Basically, it's all about trying to get the rare gas configuration. So here is an example of species, because you really can't call them atoms. I don't think you can call them atoms when it's an ion, that all kind of center around neon. And the way to think of it is you see these guys, these nonmetals, picking up electrons to become like neon, and you see these guys in the period after them losing electrons to become like neon. And they all have 10 electrons hanging out in the same configuration. They're isoelectronic. So, again, back to Thursday's lab. We talked, and you're responsible for ionic compounds, writing the neutral formula unit, and naming them. Parts 1 and 2 were just what we call binary ionic compounds, where you go to your closet, you pick a metal, you pick a nonmetal, and you throw them together. So you could go to your closet, pick metal as your sodium as your metal, fluorine as your nonmetal. So these are those Lewis dot structures where the little dots are the valence electrons, and kind of think of the symbol of the element as basically the inner electrons and the nucleus of the atom. Well, we know sodium will lose an electron. Picture fluorine picking up an electron. Sodium becomes positively charged. Fluorine, or now the fluoride ion, is negatively charged. And we have that dot, 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 awesome little, pretty darn strong chemical bond between the positively charged cation and the negatively charged anion. So that is your ionic chemical bond. Okay, we could go to the closet. Instead of fluorine, we could pick sulfur. And sulfur's 6A element, so there's the 6 valence electrons. Notice it's just itching to pick up 2 more electrons and become a -2 sulfide ion. And sodiums want to kick off an electron, so we can kind of think of it this way. In doing so, now those sodiums both become positively charged, by 1, and the sulfur now is negatively charged by 2. And then this is actually kind of, it's crisscrossing, but also down here it's showing you your neutral formula, where your pluses and your minuses are a wash. Okay, so I bet you'll do fine with this. Okay, cations, positively charged, they lost electrons. So the cation is always going to be smaller than its parent. Okay, anions, it's a different story. Anions are picking up electrons, so an anion will always be bigger than its parent neutral atom. And kind of what's at the crux of that is, again, the attraction that the electrons feel for the nucleus and the repulsion that electrons feel for each other, making it larger and making it smaller. The attractive force is making it smaller. So if the attractive forces increase, it sounds like we're back to part 3 again, doesn't it? If attractive forces increase, it becomes smaller. If they repulsive forces increase, it becomes larger.
Now, what's the unit we use for the attractive force and repulsive? Is there some kind of Greek letter?
I know the size is in meters, picometers. It's the size of the radius of the. I don't know if there is. We talked about electronegativity, but that's when atoms are joined to each other. Actually, at the end of this part 5, we are going to talk about electron affinity, and that might be kind of what you're thinking of. So I don't think that has a Greek letter. So taking a couple of metals and showing how they lose electrons. So sodium 1A loses 1 electron. Magnesium, a 2A, loses 2 electrons. And guess what? They become smaller. I'll buy that. Chlorine actually will pick up 1 electron. It's a 7A element. And shown here is to take, remember chlorine is one of the diatomic elements. So shown here is a chlorine molecule picking up 1 electron a piece to form the chloride ions. And they're bigger. So this table's kind of clever. We got the whole kind of gold looking thing and the green looking thing. They're separated by the metals, which will lose electrons, become positively charged cations, and the nonmetals, which will pick up electrons, become negatively charged anions. Okay, so here's a question. These are all isoelectronic, and if we wanted to say, switching gears, now we're going to have to kind of be a little more creative than we did with the neutral atoms. Now I'll kind of talk you through what this looks like. So they're isoelectronic. They all have 10 electrons beyond their nucleus. But if we look at what's happening in the nucleus, okay, oxygen is going to have 8 protons. It's atomic number 8. Okay. Fluorine has 9 protons. Sodium has 11 protons. And magnesium has 12 protons. So now we're talking about these isoelectronic species. Forget what I was talking about, effective nuclear charge. Just take these 10 electrons and show them pulled in towards 8 protons, 9 protons, 11 protons, and 12 protons. Same number of electrons. Does it make sense to you that maybe where you get the whole 12 protons, that thing's going to be, that's very attractive. You know, you can calculate effective nuclear charge, but it's going to be greater. I don't know. So bottom line is that magnesium species, the magnesium plus 2 cation, actually is going to be the smallest of all of those isoelectronic species. We're kind of switching gears from what we talked about neutral atoms to now we're talking about ions. So magnesium will be the smallest, followed by sodium, followed by sodium cation, followed by the fluoride anion, followed by the oxygen or the oxide anion. Now, this is a little, I don't want to throw you off or anything, but if I was going to go back to part 3 and just, I'm looking at the periodic table, just compare oxygen to magnesium, I don't know if I would ask you one of those, because oxygen, yeah, so magnesium would still be larger, wouldn't it? But no, it would be larger, and here it's smaller, if it's isoelectronic. Because we said size increases as you go down, okay, and we said size increases as you go from left to right. Okay? So actually we've talked about something in part 5 different than what we talked about in part 3. So here are the sizes in picometers, in case you don't believe me. Be like my kids. Okay. So let's take a look at these right quick, and then we'll call it a day. How's that? These will also be due on Monday. Did I look at these? I think I did. Which puts us in good shape for Unit 4 stuff. There you are. So the first one's kind of interesting. It's looking at hydrogen and helium, but it's also looking at hydrogen as it lost its proton and hydrogen as it gained a second proton from helium. And it's asking for you to say, what do you think the sizes would be like of those 4 species, basically. So just think through it. For 15, there's several problems in this set that what I did is I just went back to what are the number of protons stuck in the nucleus of that species, and I said what are the number of electrons that are giving it size. And so that's what I did here for 15, because we're dealing with 4 things, one's a cation, one's an anion, and I just get all confused. So this column is how many protons are in the nucleus, and this column right here is how many electrons are outside, whether it's a cation or an anion. So then my hints go something like this. You figure right off the bat, your smallest is going to be the one with 2 electrons, and your largest is going to be the one with 54 electrons. Then you get to wrestle a little bit with the neutral atoms, strontium and beryllium. I think they'll do fine. This one, again, there's a series of species, and I go ahead and knock out how many protons and how many electrons there are. Remember, electrons are going to give it its volume. These are all isoelectronic. Oh, forgot about that. They have the rare gas configuration of argon. Where's a krypton? Nope, krypton. Okay, so the next one looks like, oh, that was it. Oh, yay. Okay.